Good morning, everyone. Good afternoon, good evening, wherever you're joining us from. I'm Ira Feldman. I'm the MEPTEC Executive Director, and I'd like to welcome you to today's Semiconductor Industry Speaker Series that is a joint production of MEPTEC and IMAPS. So thank you for joining us. Our next presentation is on September 23rd. Ashok Krishnan Maruthi from Axeloom will talk about silicon photonics, and then we will have two presentations also in October, and we'll send you the details once we have them. But please mark your calendar for September 23rd. The webinars start at 11:30 Pacific and run approximately an hour. Also, I'm very glad to announce that next week is the Known Good Die workshop. It will be the mornings of September 16th through 18th online. Courtesy of our sponsors, registration is free. So if you have not registered yet and would like to learn more about the cross-functional challenges, so not just tests, but packaging and inspection of obtaining known good die and why it is critical for advanced packaging, please join us next week, September 16th through 18th, Wednesday through Friday, and register at kgdworkshop.org. We have a great slate of speakers, so we're looking forward to that next week. Also, please take a moment to consider supporting MEPTEC, especially during these challenging times. We have a membership available. Please join or renew. And we're also open to corporate sponsorship at multiple different levels. For more information, please reach out to Betty Cooper, bcooper@meptec.org. So today's presenter is Brandon Pryor from Prismark Partners. His presentation is Ongoing Transition to Small Form Factor Packaging and SiP. We will be recording this presentation. The video will be available this week on YouTube, and the slides will be available by early next week on our website. So let me introduce Brandon. Brandon is a senior consultant at Prismark Partners. He's been there almost 25 years and is the author of the Semiconductor and Packaging Report. He is responsible for the development of their business practice in the area of semiconductor packaging technology, along with research projects in that area. And over the years, Prismark has developed business and service relationships throughout the industry. Brandon has a BA and a BE degree from Dartmouth and the Thayer School of Engineering. So with that, we welcome Brandon.
Okay, thanks, Ira. So again, as Ira mentioned, the title of my talk is the ongoing transition to small form factor packages and system in package. So we'll be looking at historical trends of adoption of new and smaller form factor package technologies. We'll be taking a look at adoption and technologies being utilized in system and package, and then also look at some of the future directions in terms of what people have been thinking about and working upon, primarily on the small form factor side, but also within advanced packages for system and package approaches. I will reiterate that what Ira just mentioned is that although this is a one-way discussion for the most part, I believe there's a chat window for you guys to ask questions, which Ira will moderate as I go through the presentation. So first, a bit of a backdrop, looking at, I guess it's now almost 30-year history and a bit of a forecast, both on system level and semiconductor level growth. And this shows in a time periods of 7 years. We've selected 7 years as a way to hopefully even out the peaks and troughs of the cycles that we see in our industry. But basically shows that the growth rate at a system level, which has varied over time in the mid-single digits for the most part. But as the industry matures, it is indeed slowing down with faster growth coming from certain segments. So certainly now there's a lot of excitement, enthusiasm about 5G, cloud and AI, data center, autonomous driving, and IoT being the key drivers. But underlying systems like PCs, smartphone, just servers in general continue to be major growth drivers. Kind of towards the bottom of the graphic there, we see line items looking at the semiconductor value, which back in the 1990s was growing at 3 or 4 times the growth rate of the system number. And although that's slowing, we do see continued strength within certain segments for that. Likewise, the IC unit growth rate has been slowing, and part of that slowing growth is not because there's fewer components per system, but just the amount of integration that's happening both through system on chip as well as the use of system in package. So even though there may be more and more die shipping and more die area, here we're counting finished IC units as package count in terms of that growth trend. So again, slowing growth, but we'll look at some of the faster growth segments within that.
Okay, so Brandon, just a general question. How large is the data center slice? And you're probably going to touch upon it, but you know, there's this whole concern that nobody's reporting statistics on data centers as far as the number of servers or silicon shipped to data centers.
Yeah, a good point. So let me add 2 questions there. So how large is the data center segment? So data center is a portion of the computer piece of that. Off the top of my head, the data center segment is about $100 billion market. So out of the total, it's actually quite small. What's interesting about the data center market is that the semiconductor content is extremely high. So a server made by Google or Facebook, assembled by Quanta or Compal, the semiconductor content may be as high as 80% of the system value. Compare that to an automotive electronic system where the semiconductor content might be as low as 10 or 15%. So it's still only about 5% of the overall value. It is a faster growth segment. The second question was, is it being underreported? In some cases, you may argue it's underreported because the system value is never really reported. It's only the semiconductor content is. And that's why when we look at some of the value growth at the data center side, we're looking at not just the growth of Dell or HP, who are relatively small players in that segment, but the growth of Quanta, Compal, Inventec, Inspur, who have heavy growth in that, and then the semiconductor players, Intel, AMD, NVIDIA, and then a presumed amount from guys like Amazon and Google and Baidu that make their own chips. So looking at where we see fast growth, and here we've got, you know, almost a couple dozen different categories of products that are growing relatively fast. So these are all multi-billion-dollar segments within segments. So, you know, we have subsegments of PC, subsegments of servers, subsegments within communication infrastructure, but those are already multi-billion-dollar markets, and they're growing at double-digit or near double-digit growth for all of them. And the key point I wanted to take here was, you know, the majority of these, not all of them, but the majority of these, certainly AR, VR, certainly the PC and smartwatches, certainly SSD, certainly home automation, certainly ADAS systems, all of these have SiP integration. And if, you know, that's, you know, driving continued growth of SiP. And again, people often think about SiP as being driven by wearables and maybe mobile phones, but the reality is it can be used across many of these other applications. So, you know, thinking about the data center segment, what this slide shows is even though servers might only be 10%, or data center, in fact, might be only 10% of the overall electronics hardware, when we look at the total combined servers, data storage, communication infrastructure, which includes 5G, but also includes networking within a data center, that does represent today about 25% of the overall semiconductor content. So again, much higher than that 10% that I talked about. But again, this includes enterprise servers, it includes storage for a variety of end applications, and it includes communication infrastructure, both for wired and wireless, which again is enable or being driven by the data center, but not necessarily located inside the data center. And that continues to be the fastest growth segment overall. So we see combined 8% compound growth for that over the next 5 years. Again, comparing that to the relatively mature PC and computing side, mobile phones and tablets, it's much faster growth than those overall. Getting to the discussion related to packaging. And again, here we've got 20 years of history, 10-year forecast. This is really just showing the really big picture trend in terms of what we saw going back 15 years ago, which was the migration away from lead frame packages towards array-based packages. Again, this is all on a unit perspective, not in value terms. If we looked at value terms, the BGA packages would have much higher share than this. But what this is showing is this continued ongoing trend towards wafer level, shown in the red there, bare die for chip on flex, chip on glass in the pink, the array-based packages, which are in all of the yellow and green and orange segments there, as compared to the lead frame packages. But again, keep in mind, we're talking units, and QFN, which are still an extension of lead frame packages. These support any pin counts ranging from 2 all the way up to 200. So they support a much broader range of products and will continue to grow in the foreseeable future. Again, a pitch here looking at wire bond versus flip chip. Again, a lot of people have been talking about flip chip as the predominant way to go in the future. But even out in 2030, we still see on a unit level, not in value terms, that wire bond will still be about 70% of IC package by unit count in 2030. And that transition towards wafer level and flip chip continues, but at a slower rate.
So what keeps the wire bond technology alive? I mean, you'd think at some point these parts would be obsoleted and they'd be replaced with flip chip or I mean, the number of new designs going into lead frames, is it about the same, or is it?
Yeah, I mean, yeah. Okay, yeah. So I mean, in talking to one company, and I think they're not alone, still about 50% of their new designs go into QFN packages. So this is not an NVIDIA or an Intel, right? This is a analog power IC type company, but they're not alone. Their partners are also similar. There's just a lot of need for that. What's keeping wire bonding alive is simply cost. Still at less than 100 IO, wire bond packages can be significantly cheaper, not can be. So there's still a cost premium associated with flip chip. And so if there's not a requirement for flip chip for performance or for form factor reasons, most people will continue to utilize wire bond. And in fact, I mean, there's a whole spin on this, but in the last 10 years, there's been or maybe 15 years, there's been this transition from gold wire to copper wire, which is enabling wire bond to still be less expensive still.
Thank you.
This was just showing a comparison of the different package technologies as more from a educational perspective. But again, just looking at where wire bond lead frame packages fit, they basically fit into the domain of anywhere from 2 IO to 200 IO, and they're cost effective in that range. The wire bond BGA and CSP packages fit anywhere from 40 to 800 IO, and again, that's not meant to be all inclusive, but that's a general idea of where they're most likely to be used. And then the flip chip CSP or BGA packages fit anywhere from 300 to 2000 IO, and in fact, a few companies now have 5,000, 6,000 IO type packages being used. The wafer level CSP, I think somehow the picture cut off that, but we'll see wafer CSPs anywhere from 3 up to about 300 IO today.
So there was actually a question, or somebody commenting that QFNs are not necessarily wire bond packaging. It's only there are flip chip QFNs. So is that a significant piece of the QFN market, and what do you expect the growth to be in that area?
I don't recall the numbers off the top of my head,
Right.
but yes, a small sliver of this chart of QFN or flip chip QFN, let's say it's less than 5% of the volume. It may be even less than, anyway, less than 5%. It is growing a bit faster, but the people that are using flip chip QFN are, again, doing it for two reasons. One, because of a performance reason. So for a 5G transceiver chip, for example, where they have to do that, we've seen some high frequency RF components using flip chip QFN. And then there are a few companies that use flip chip QFN because it actually enables smaller size. So you can actually have the die size close to the package size with the flip chip QFN. And it's thinner too. But again, it's a fairly sizable price premium for smaller size. And people will use that in some cases where they don't want to use fan-in wafer level CSP.
Thank you.
This next chart just gives a nice picture of, you know, not just Apple's phones, but other leading flagship phones. I'm not sure why we have Huawei, not two Huaweis and a Samsung phone, but if you saw a Samsung phone, it'd be a pretty similar story there. But the red box there basically outlines the size of the overall main board assembly. And the main board assembly basically houses, for the most part, all of the RF and digital components. So all of the memory, all of the chipset components required for that. These are often now, it's certainly in these three phones, as stacked board assemblies, which we'll see a picture of on the next slide for that. But you can see in general terms, you're talking about 15 to 25% of the XY area is taken up by the main board assembly, but it's actually less than 10%, and in some cases as little as 5% of the volume of the phone is accounted for from the main PCB and all the packages and the EMI shields on those packages. All the other volume is for air, for the display, for the case, and for the battery. So this is an example, and whether you take apart a Samsung phone, a Samsung flagship phone, a Huawei flagship phone, an Oppo flagship phone, or an Apple flagship phone, you will all see often use of stacked board assemblies. So on the left-hand side there, you have the RF section as a stacked board assembly. It's basically soldered down onto the primary board assembly for that. So you have those two boards. Depending on the supplier, you may have double-sided assembly for both boards. In this case of the Huawei phone, only the primary board has double-sided assembly, and then the RF section is just a single-sided assembly on that. But the Apple, for example, will have double-sided on both of the boards. But again, that use of stacked boards combined with SiP and small form factor wafer level CSP packages enables this continued functional capability in smaller and smaller form factors. So the main boards of the PCB, although right now they're actually getting bigger to accommodate 5G, but on average, the main PCB board area in total has been shrinking over time.
Where does, you know, these are all high density printed circuit boards. I mean, where do you sort of see the boundary between the high density PCBs and, let's say, package laminates? I mean, they're starting to get close in terms of line space, micro via construction and things like that. Are they not?
They are getting closer, but depending where you pick your points. So this Huawei phone, the minimum line spacing is probably about 40, maybe 35 micron line spacing. A leading edge Apple product will have as low as 25 micron line in space, all using, in Apple's case, using MSAP type processing. However, on the package substrate side, you'll see sub 10 micron line space. So again, depending where at the leading edge. But yeah, there certainly is a domain around 20 to 30 micron line space where main boards are using that and some package substrates are using it. But at the leading edge, the package substrates are still far beyond, and the level of investment required is significantly different.
Okay, thank you.
So what's enabling the smaller size systems? Of course, system on chip is a big part of that, right? But in addition to that, you still have the die size, and a lot of these packages is quite significant. The I/O counts continue to go up. So what people have been doing is to keep the package sizes the same or smaller is the adoption of finer pitch components. So over 10 years ago, companies started adopting 0.4 millimeter pitch components. At the time, I think Qualcomm called it NSP, which I guess stood for nanoscale package. The terminology kind of went away. Now 0.4 millimeter pitch is quite common for CSP packages. Over the last 3 years, we've seen companies adopt 0.35 millimeter pitch, started with the application processor, but now used in many other components. We've seen a lot of development to support 0.3 millimeter pitch. Certainly the test sockets have been there for a long time, but the SMT processes, equipment, materials have been developed. But as far as we've seen from our product teardowns, few seen on the market, most of the volume has been driven by Apple and their watch and AirPod products, where we see down to almost 200 micron pitch of the components on the, I'll call it the main board assembly. Apple calls it, in fact, an SiP, which we'll talk about that system and module type solution later. Again, a lot of the semiconductor suppliers would like to move to the finer pitch, but the limitations are still there related to PCB routing, package level test, and the assembly capabilities for those. Although Apple, the leading edge guys, including Apple, are pushing to 25 micron line space for the HDI main board, the majority of products are still at 65 to 75 micron line space. And therefore, people continue to use these fan out either wafer level packages or traditional laminate based packages to leverage the 0.35 millimeter pitch package approaches. So for beyond portables, I think most people understand that the majority of the volume for fine pitch, for advanced HDI technology is still being driven by the smartphone market. Beyond portables, a lot of companies really just don't see a need for very small form factor systems. So even in the smart speaker, for example, there's plenty of room inside there to have 0.5 millimeter pitch, and in some cases might be considered. Most people remain a bit adverse to advanced technologies because any advanced technologies may reduce assembly yields and reliability, sometimes limited supply chain of the PCBs or the testing capability. And there are still companies that would prefer to stay away from the exposed die wafer level CSPs, which can have die cracking or other issues associated with that. And all those have been resolved in many regards, but again, the notion is concerned about that. So again, if people don't have to go to size reduction, they don't have to use these advanced packages for performance reasons, we'll see that transition becoming a little bit slower. However, in some cases, they want to go through size reduction mainly because they can reduce costs of the overall assembly by reducing the PCB area, reducing the package size, and they would do that as long as there's no sacrifice for reliability or any limitations from the supply chain side. So this chart gives our perspective in terms of volumes of array packages. So this includes BGA, CSP, fan-in and fan-out wafer-level CSPs. This would not include any components that go inside a package. So it's not going to be any bare die flip chip. It doesn't include chip-on-flex or chip-on-glass for display drivers. So it's all components that are mounted directly to the main board of the system. And this just shows, already since 2014, we've seen 0.4 and 0.45 millimeter pitch being adopted, and that continues to grow. But because it's limited to smartphones, the majority of other products continue to use 0.5 or even down to 0.8 millimeter pitch. We're now in the transition to this 0.3 and 0.35 millimeter pitch, and that will continue to grow. But again, it's still only used for certain components and for high-end smartphones. So not just the flagship phones, but a lot of the lower-end smartphones will continue to use just 0.4 millimeter pitch components. So switching from just finer pitch and smaller form factor packages to SiP. So again, a lot of confusion about what defines an SiP. We try to make a nice clean definition, but the reality remains is that there's a lot of gray areas in terms of what's SiP versus a module. So a module basically can contain one or more bare die or other components to form a functional electronic block. That module, in fact, could be connected like a package, or in some cases, like a camera module or a fingerprint sensor, it's connected with an actual connector. So that's the difference between an overall module versus that. A system in package is basically a subset of modules, which would be any of those devices that go into a surface mountable device. So it could be, in fact, a lead frame package could be an SiP, a BGA, a CSP, LGA, and anything basically that's surface mountable, or I guess it could be socketable as well, could be an SiP. Most common examples of SiP by volumes include RF modules. So this could be power amplifier plus passives and switch chips. Could be connectivity chips for wireless LAN or Bluetooth. Could be memory packages, which would be stacked die, which could integrate the controller within them. MEMS and power devices, perhaps shouldn't have put those together, but with integrated controller inside the package. And then finally, and I'm not going to be talking about it too much today, but these large BGA packages with multiple die and or memory, and in the future, perhaps transceiver or silicon photonics devices that go into those. And a lot of decision making goes into adoption of single die versus multi-chip packages. But again, that's driven by the size and form factor, thermal management concerns, complexity of testing, cluster device for electrical performance. In a lot of cases, it makes sense for these PA suppliers to create a complete functional module for the end customers. So companies like Skyworks, Avago, Broadcom, Qorvo, these guys have been doing RF modules for 20 years, and it's just a logical approach for their end customer to integrate a fully functional and tested system for them. So next slide here looks at some, but not all, of the SiP volumes. Again, this kind of highlights the big volume products or high value products out there in the market. In a lot of cases, they're kind of bundled together. But basically memory, which is primarily stacked die, often with controller, but not necessarily, and that could be NAND, DRAM, or both within that. That's a pretty significant use for the majority of NAND go into stacked die devices. The majority of mobile DRAM go into stacked die packages. And certainly in the case of NAND, more often than not, we'll have an integrated controller with those. So close to 9 billion packages in total. And that's a very sizable a portion of the all NAND die going into that. Package on package is another critical one that's been adopted for baseband and more likely application processors and mobile phones. That one's not necessarily growing, and it's because in a lot of cases, the mid-end phones have gone to a single die package approach for those. The RF modules, which includes the power amplifiers, the filter-centric RF modules, and the connectivity. Again, very significant volumes in total from there, so over 9 billion total packages. If you include all the RF modules, again, very small form factor, heavily driven by smartphone, but increasingly used in notebook and IoT type applications. One of the SiP that's been getting a lot of attention recently has been these antenna in package modules. I'm not going to spend too much time on that today, but that's certainly a fast growth driven by the millimeter wave products, and a number of phones have adopted those today, and we'll continue to see a lot of growth over the next several years.
Well, with the 5G, are we likely to see more than one SiP, one for, let's say, the sub-6 gigahertz and one for the millimeter wave in a system, or do you think they'll eventually cram both the millimeter wave and sub-6 gigahertz into one package?
That's a good question. I'm not sure I know that answer. But let's just, what I do know is that the antenna package for millimeter wave, today, there'll be 2 or 3 per phone. There's actually quite a lot that goes into that. It integrates the antenna, of course, for that. It also has the transceiver and PA all integrated into that module for that. For now, the sub-6 gigahertz transceivers are separate. The sub-6 gigahertz PA are separate. And so for that reason, we're seeing as many as 10 total RF modules, if you include the PA, the filters, the connectivity, and the IP in the leading edge 5G millimeter wave phones. And that's historically been 5 or 6. Low-end phones might use 2 or 3, but 10 is a pretty big jump. And yes, there'll be in the future integration, and I think also in the future as people phase out 2G or 3G bands, there'll be fewer modules as well. But yeah, it's an ever-present challenge in that the RF section of the mobile phones continues to get larger and larger despite the efforts to create these fairly well-integrated SiP. I mean, I don't know what the latest iPhone will support, but leading-edge flagship phones support as many as 100 bands today. So it's a pretty significant feat that they're trying to deal with. And I mentioned here, out of 250 billion ICs that chip, SiP already represents about 50% by units, but over 30% of the wafer area. And that 30% is heavily driven by a couple segments, the memory SiP and the CPU, GPU segments, which have very large die, and in the case of the memory, stack die being used for those.
So a question came in on what's the major use or market of the power SiP?
The power SiP is kind of all over the map. It can be from a very simple application in a mobile phone or notebook application to a much more complex power module or power package for an automotive EV type application. So it's a pretty broad range of products for that. Typical would be the mobile phone just by volumes, but by value, it's really all over the map.
Thank you.
And that's why it says all for key technology drive. So a good question, but the highest volumes of that 5 billion, it's going to be the mobile products, but the value ones is going to be in automotive and other high power applications. So again, I picked a few typical examples of these RF modules. This one's from Avago Broadcom, a front-end module, I think found in an iPhone, but I think very similar modules you'll find across all the mobile phone suppliers. So here it's a front-end module that's supporting multiple bands, multi-band, multi-mode. And this is all squeezed into an 8x6 millimeter, less than 1 millimeter height BGA module. You have components mounted on both the front and back side. You have passives squeezed in between the solder balls, as well as even some components shown in the bottom left-hand side of the bottom image there. You have flip chip die, SMT passives, filters, wafer level capped filters, all integrated into that. And that's put onto a 9-layer substrate that then also has, once it's overmolded, you have an EMI shield put on top of that. And actually, as shown in the top right-hand image, you actually have these compartmentalized EMI shields put into that. So quite a lot of engineering effort goes into this to be able to, one, integrate all those different components, support all the different bands, and then also have some EMI shielding within this quite small form factor package.
Is the overmold metallized to get you the can effect or the shielding, or is it just that they put additional metal in to make the compartments?
No. So two things are happening here, and unfortunately, I don't have my additional picture that goes along with this. Okay. The EMI shield is actually sputtered on top of the mold compound. So it's a sputtered material that's done on top of the mold compound. It's actually done fairly efficiently. The components are just put in a big tray and put into a sputter chamber, and they can do hundreds of packages at once or thousands of packages at once. The other thing that's happening here is that they do have some compartmentalized shielding there, so they sewn off some areas. What's not shown in here is to create the walls, the vertical walls between the components, is there's actually wire bond loops. And unfortunately, the X-ray doesn't capture that very well, but there are wire bond loops in those spaces between the EMI compartments to create that Faraday cage there. So it's actually something that Skyworks has been doing for many years. Now we see other companies adopting as well.
So wire bond will live on. Okay.
Yeah. So yeah, even though there's no wire bond packages here, there's actually wire bonding done within this module. And another thing that people think about is Apple's quote SiP. So Apple with their Apple Watch back in 2014 kind of came out with a revolutionary solution where they're doing kind of package level interconnect in their main board assembly. And they call it their SiP. In fact, it's really more of a system and module because the whole system is inside that module, and it's that SiP is not actually surface mounted to the main board. That SiP is the main board. Again, a little bit tricky terminology, and people call it SiP because that's what Apple calls it, and I can't argue with that. But again, I call it a system and module here. This uses an advanced PCB technology to achieve 25 to 30 micron line space. You have bare die or wafer level CSP components down to 200 micron pitch. You also have some flip chip CSP components that are assembled onto the main board. You also see that solution not just in the Apple Watch, but also in the AirPod products as well. Most other companies using smartwatch still use traditional SMT and HDI, or sometimes the use of rigid flex PCB assemblies to adopt that. And again, that substrate-like PCB, which was quite revolutionary back in 2014, is still predominantly used by Apple for their watch and mobile phone products. Samsung and Huawei had released a couple products using that and more advanced PCB technology, but not adopting it in as big a way as Apple has done. So again, we do expect growth of that, and that will enable smaller form factor within wearables, smartwatches, fitness bands, AR and VR devices within those.
So a question that came in with that 25 micron line space HDI, you talk about the MSAP processing. Is that really are these being built on, let's say, IC packaging equipment, or are these built really in PCB sort of, huge panels?
It's a mix. So it kind of depends where the company came from. The former TTM operation, and forgive me for the new name of the company that the Chinese company bought them, AT&S, Ibiden, at least their operation, those guys have a more larger panel PCB type processing. Other companies like Simtech, Compact, they came really more from their packaging development line. So it's kind of a hybrid of concepts. In the end, most of them use pretty similar equipment, but the equipment sets are mixed, some from the traditional PCB-like, some from the package-like assemblies. But again, the level of investment was quite significant. Apple convinced, I think, 7 or 8 companies to invest quite a lot of money in this MSAP type processing. Today, 4 or 5 of them represent the majority of the volume capability. It just wasn't a profitable business for a number of them. And I think most people hoped beyond Apple would adopt it. And again, I'm not trying to call it Apple in a negative or positive way, but certainly they were the guys that initiated it 6 years ago, and still waiting for other guys to adopt it in a major way. It's just, it is an expensive approach, and not everyone sees that as a necessary route to go. So keeping the Apple theme in mind here, here's the Apple AirPods Pro SiP. And again, you can see the relatively complex assembly. There's system on chip die in there. There's SiP packages on this SiP module. So there's a lot of confusing terminology within that. But basically on the bottom side, you have a MEMS SiP. So that's O, N, and P there. You have another SiP with that. It's the actually main ASIC chip. That's the H1 SiP with memory plus passives on the bottom side of that. And that's all integrated into this larger SiP, which again, it's not really an SiP, it's the main board of the system, but it integrates all that. You have bare die, some very small passives, plus other packages mounted onto that assembly. And again, it's a key enabler of these very small form factor earbuds that Apple has built, and other companies are building something kind of similar, but not quite as aggressive as Apple today, at least so far. Again, as a comparison, here's older generation, but still a Samsung Galaxy Buds that are using just a rigid flex circuit, combination of SoC, other SiP packages on there, but a more traditional SMT assembly onto a, again, high density rigid flex assembly for that. But again, many fewer components, much larger form factor compared to the Apple approach. And you know, Apple is not standing still. This is just showing the Apple Watch S2 from 3 years ago compared to the Apple Watch S4 from last year. We do have the S5 as well, but this was just a good comparison photo in similar form factor. And I don't show the metrics here, but I think it's quite obvious from the image that the level of complexity within this has gone up 2 or 3x. Again, here, the Apple S4 integrates LTE, whereas the Apple S2 did not. And certainly the amount of components and the pitch of the components is also reduced in that time frame. So again, in Apple Watch S4, I think we saw down to 0.22 millimeter pitch components for some of them, and a number of components of 0.3 and 0.35 millimeter pitch.
So a question that is not necessarily Apple Watch specific, but asked about embedded components, actives or passives in the substrates. Are the SiP modules using them increasingly, or is that still sort of, you know, it's just still easier to put it on the surface? Well, what's happening in terms of embedding?
Yeah, so embedding still remains, after 20 years of development and technology interest, a relative niche solution. About 5 years ago, there was a pretty heavy adoption of embedding passives into the application processor and other CSP packages. There are a few notable design wins of embedded die being done today, but the volumes are relatively low. I believe also one of the major OSATs, I'm not going to call them out because I'm not sure how public that was, kind of just shut down their embedded systems operation. So I think people have found that while embedded is a good idea in concept and it saves a lot of space, it's a 3D packaging without going to TSV. Going to a route which uses conventional packaging, just smaller form factor, pitch, and or system and package without going embedded is a much easier route for most companies to do. That being said, there were probably 2 billion embedded die shipping last year, right? So it's not insignificant. It's just the value of it is often with very simple devices. And there are a lot of programs ongoing now in China with Founder Access, Shenin, I think it's called Skychip. These guys are all developing panel level embedding die solutions. So it's not dead, but it's, from a value perspective, we don't see it that often. This was just another one, just highlighting the 0.4 down to 0.3 millimeter pitch components from the Apple Watch Series 3 for that. Again, you know, this picture was a much more dramatic transition from a 2-year time frame or a 4-year time frame as opposed to this just one example in between those. So where do we go forward from here? I think that people recognizing that there are a lot of good capabilities out there already today from OSATs, from IDMs, from wafer foundries for supporting a variety of processes to integrate various components. Today you have anything including logic, memory, power, MEMS, passives, RF, photonics that can be integrated within to a single package. You have a lot of applications that have different requirements in terms of reliability. So mobile and IoT were certainly the big drivers in terms of volume, but reliability requirements from a medical or automotive, and certainly from the high performance computing and aerospace, will drive very different requirements for that. The idea of integration, whether you call it MCM, SiP, heterogeneous integration, is not new, but the increasing complexity that we see, the varying process options, substrate technologies, interconnect technologies is certainly quite a bit overwhelming, as we saw in some of those pictures. Again, a lot of people tend to leverage the ongoing know-how and capability, but there are certainly a lot of things that we didn't talk about today where people are thinking about, like 3D TSV, which is being used for image sensors and now increasingly for logic, 2.5D with silicon interposer, fan-out wafer-level packaging, all of which can enable finer geometries and more elegant designs compared to the traditional packaging approaches. So summary, without a doubt, we see ongoing evolution. So again, that refers to continued pitch reduction, continued use of both wire bond and flip chip interconnect to enable that ongoing functional improvement. That from a volume perspective, it was initiated by smartphone, but continued extending adoption in tablets, notebook PCs, consumer products, and certainly more for those. We see both wafer level and SiP approaches being adopted, in some cases in combination for those. One thing we didn't really hit upon today, which I'm sure that perhaps the next presentation we'll talk a bit more about with silicon photonics, is that at the high-end side, and certainly there's been a huge amount of investment related to large-size BGA substrates, 2.5D technologies, a variety of other alternatives like the FO-WLP from TSMC, Intel's EMIB package technology, where they're integrating very complex logic with memory or high bandwidth memory technology. And there's certainly a direction in the future to add photonics, transceivers, and in some cases already being done so today, and the future for those. So I think that ends my presentation there. I realized there was probably a lot to absorb there in terms of content, and I probably left some open-ended questions at the end there to keep people thinking about this, and maybe to contact us or others to see what's going on. So I think now if there are other questions that people have, I'll let Ira field those.
Yeah, they're starting to really come in. So thank you, Brandon. Everybody, you'll see in a moment a poll pop up on your screen, so please take a moment to fill that out so that we get some feedback. And as I said, the recordings will be available later this week on our YouTube channel, and the slides will be available early next week. So some questions, and this one you can, of course, answer as a plug for your consulting, but there is somebody who's asking, do you have an updated breakdown for DRAM memory packaging as far as how much DRAM is being wire bonded, singly stacked, or 3D? If you want to talk at a high level of that, of course, that's good. But
yeah, I mean, for DRAM, the majority of mobile DRAM is still wire bonded and still stacked. And the stacks can vary into 2 die, 4 dies, sometimes stacked side by side to reduce height a bit. For traditional DDR, so DDR4 mainly today, that's Samsung converted to flip chip a while ago. SK Hynix and Micron are in transition to converting to flip chip. For graphics DDR, that's all been flip chip for some time, and that transition and that growth continues for GDDR6 as all flip chip.
it makes sense. There was a question here in terms of fan-out wafer level packaging. Do you consider that embedded die, or how do you characterize fan-out wafer level packaging in terms of your nomenclature?
Yeah, so certainly today we separate out fan-out wafer level packaging as using an RDL type process, and that could be on a wafer or on a panel size solution. Embedded die would utilize traditional laminate materials So like a BT, laminate, or others. In the future, there may be some confusion because people might use PCB type processes with dielectric type materials and vice versa. They can use Ajinomoto type materials for panel level fan out. So there are some gray areas in that, but that's how we separate is fan out wafer level package use wafer based materials. So meaning spin on dielectrics or film slit coated dielectrics as opposed to traditional laminate or prepreg materials.
Okay. I think that should answer that one sufficiently. There was a question, could you confirm, on the IO count for the WLCSP slide, what the number was again? That was
so wafer level CSP, wafer level CSP, you'll see, again, this is in fitting with the other segments, 8 IO to about 300 IO. You will see some 4 IO wafer level CSP, you will some that are over 500, but I think 8 to 300 is the predominant domain.
Okay. And let's see, in terms of, wow, they keep coming in. Is there any comments you can make on new packaging material in terms of supporting high millimeter wave or thermal conductivity or better CTE matching that you're seeing on the horizon, or general activities in those areas?
I would say there's quite a lot of activity. So without trying to name all of the major material suppliers there, all of the big guys, which includes Mitsubishi Gas, Panasonic, Hitachi Chemical, or former Hitachi Chemical, Doosan, all these guys have developed over time lower loss, lower CTE. What was the third one you mentioned? Improved materials out there in the market to be able to support millimeter wave. Higher thermal conductivity. Right. So it's not always to get all 3 of those characteristics at the same time, but they're all working to develop improved prepreg and laminate solutions, and many of them have been adopted. A number of them have been adopted not just for the package substrates, but also for the main board assemblies as well.
And of course, customers want all 3 faster and cheaper than previous. Yeah, it's the usual. What can you comment on reliability requirements for like aerospace defense? Do they slow the adoption of these advanced packaging technologies, SiP, or?
Do they slow the adoption? Well, I mean, in fact, probably before my time, the first SiP, I believe, were used for aerospace or satellite applications. And someone might have called that a hybrid or an MCM at the time, but they don't. They are often big proponents of that because they don't. Well, traditionally they didn't like mold compound or laminate, so they wanted to take bare die, put them all together on a piece of ceramic and build an SiP to suit their needs. So I think the question probably comes from, are they slower to adopt these cost-effective SiP? And the answer is probably yes, because they're not reliable enough for their requirements.
Right. Let's see. Okay. There was a question, if you would go back all the way to slide 4 with the divisions between the segments. The comment was that they look pretty similar between 2019 and 2024 in terms of sort of overall percentage. Is some of the growth being masked by either the segmentation or things like medical within industrial, medical era? I mean, I know you talked about some of the high growth segments or the sub segments, but looking at the charts, they look sort of the same. It's just the size of the pie grew bigger.
Right, the size of the pie grew bigger. So that's why the bar chart at the bottom kind of shows the relative growth. And I mean, whether you're growing at 3% or 8%, is that really that big a difference? Not so much, but that's what happens when you have a kind of a mature industry. So today, when people talk about 5G, that's a big growth driver. But 5G drives phones, it drives in fact computing, it drives server storage, and it drives communication infrastructure, and some might argue it drives automotive electronics and consumer electronics, and industrial and medical, right? So 5G really is pretty much everywhere in there, right? You know, and IoT, same thing. IoT can be a subset of a you know, mainly in consumer and industrial, but IoT could also be argued to be within some other segments. So the fast-growing segments that I think we mentioned on the previous slide, you know, filter across all those big ones. And that's why, you know, if you're looking at it from a big picture, it looks a bit skewed. You know, somebody might say, oh, 5G is driving mobile phones. Yeah, well, 5G phones are going from 20 million to 200 million phones this year. That's great. But 4G phones are going from 1.4 to 1.0 billion phones. So you have to kind of keep that in perspective.
Got it. Okay. Let's see. Wow. There's probably more questions. I think we'll leave it there. There's more questions than we have time to answer. Brandon's contact information is on the last slide. I'll send him the list of questions, and I'm sure you could reach out to Brandon directly and discuss if there's something he can help you with in particular. So thank you very much, Brandon, for presenting today.
Sure.
Let me grab the screen back from you. Thank everybody for joining us today. And a reminder, our next Semiconductor Industry Speaker Series presentation will be on September 23rd from Asha Krishnamurthy, who's the CTO of Axeloom, who will talk about silicon photonics. Also, don't forget that the Known Good Die workshop is next Wednesday through Friday. Registration is free, courtesy of our sponsors. Please join us for this cross-functional look at what it takes to do advanced packaging and known good die at kgdworkshop.org. And with that, I will wish everybody a good rest of their day. And I thank you all for joining us and look forward to seeing you at a future MEPTEC event. Thank you.